So hello, everybody. Thank you for attending our presentation, and thank you, Becky, for introduction. So my name is Taras Dekun. I'm a sales engineer at MEA Incorporated. Today, we'll talk about rethinking FCC actuation and controls. So agenda of our presentation today will be overview of the current technology on FCCU catalyst slide valves, talk about alternative technology, compare alternative to the current technology, and then hopefully you'll have some questions that I can answer. So the focus of our applications is slide valves and butterfly control valves around FCCU. So basically, we're talking about region catalyst slide valves, spent catalyst slide valve, double disc flue gas catalyst slide valves, catalyst cooler, recirculation, and then inlet expander and bypass expander valves around the actual expander. So depending on a type of FCCU unit you have some of the valves you have, some of them you don't. So for many years, these actuators already require to use electrohydraulic actuation due to the fact that you need to properly operate the valve, as these valves are super critical, and they basically control temperature, pressure, and the level of the catalyst and the whole process within the FCCU. So these valves are required to be required to provide extreme accuracy of positioning, very high speed. Also additionally requires the ESD, really high speed ESD. And further, of course, these valves are required to be really fast. So all of these items and requirements put only one choice to use on these valves are electrohydraulic actuators. So basically, let's see what we actually currently use on these valves. Basically, at this point in time, you have some type of hydraulic power control unit, which is getting connected to the actual actuator. So usually you have this type of setup where you have mechanical override connected to the valve, and you have a hydraulic cylinder, which is also connected to the stem of the valve to position transducers. Then this cylinder getting connected with the hoses to hydraulic power control unit, which basically looks something like this. So how it actually works, we take the hydraulic fluid from reservoir, pump it through the motor pump assembly, basically build up hydraulic pressure, put it through the filter manifold and charge the accumulator. And then we use this charged accumulator energy, basically, which is stored in as hydraulic pressure, and send it through the main manifold, which basically sends the fluid into one side or the other side of the cylinder. All of this is basically getting controlled by some type of PLC-based controller. We basically monitor the position of the valve and then comprehend the signal, position the actuator to the proper location. So quite a lot of things in this quite complex units. And basically, how did we get to this point? So a brief history. MEA have been building these units since 1960s, actually. So before, there were these big self-contained electrohydraulic actuators, which were very similar to the current design. They had identical components. However, they didn't have all the redundancies and additional componentry the current units do. And however, they worked well and for quite some time, about 20 years. Then we realized in the 1980s, 1990s, we started splitting up the actual hydraulic power control units and actuator portion, and then connecting the hydraulic hoses. So that was done to be able to eliminate all the tough work and maintenance on these units, as you had to really take off this self-contained unit away, and then you had to actually work on it. It's really tough to work on them. So we basically separate them out. At the same time, we got another problem now. We had to run the hydraulic hoses and additionally find the additional space on the deck. And in 2000 up till today, these units got even bigger. So currently we added numerous of redundancies all around the place. basically position transducer, pumps, additional filtration systems. We added about 8 to 10 different transmitters to be able to monitor all sorts of pressures. And of course, it comes with now with different type of PLC, single redundant, triple redundant. So as we can see that these units progress from bigger to even biggest over time. However, we wanted to ask the question, so did they actually become more reliable? Maybe we should just stick to these old units, that self-contained units, which were built 40 years ago. And we actually have about 40 of these units still installed in the field. And they are over 40 years old, zero redundancies, single analog control boards. However, they work and they work well, as you can see, if there is so many installed still. So let's investigate what have changed and what are the main causes of failures. So if we actually look into our different manufacturers and you look into the main common problems within the unit, you actually see that all of these problems are common between all of these HPCUs. So first of all, we see the fluid cleanliness here. So fluid cleanliness actually, and if the fluids get contaminated, it actually affects the performance and malfunctioning of the components, which is one of them is the servo valve. So if there is there is a lot of debris in the fluid, the servo valve have this little filter in it, which is getting clogged, which caused the malfunction and then valve drifting. That's the main issues. And we see that that's the issue for most of these units. It doesn't matter who makes them. Additionally, you always have internal leakage over time. There is a lot of tubing. There is a lot of high pressure hosing around, which runs back and forth. So if the seals deteriorate or fitting get loose or whatever, you get a leak. Additionally, you of course get pump failures, electronic failures. These are basically common things. And but as we look, we all got the same basically problem with these hydraulic power control units. So how did we actually try to improve these reliability of these units? So let's look from the beginning, where we had self-contained electrohydraulic actuators. Then we went to our analog-based power control units, and then we talk about PLC-based skids. So let's go one by one and figure out what's been improved and what's not been improved. So we talk about redundant motor pump assemblies. Yes, it's been improved because before we didn't have redundancy, now we do. So if you now have pump failures, you can go back and actually operate the other one. Dual filter manifolds. So those ones, the older ones had one. Current units actually have a kidney loop filtration system with these units, one of the newer ones. And yes, we improve in the fluid cleanliness, for sure, reliability improvement. Redundant accumulator banks, additional improvement. Current units have numerous of accumulators, which in case of one, the other one come back online and operate well, definitely reliability improvement. Redundant control manifolds. So this one's actually, we did not put any improvement in this side. So as you remember, our servo valve and our componentry around the main manifolds are actually one of the most critical ones. However, we never addressed this item. Okay, let's go farther. For now, ESD system, online ESD testing, definite improvement. Went from 1 out of 1 to 2 out of 3 now. And of course, we can online test it as many times as you need to now. Definite improvement. Redundant position transducer, additional improvement. Control systems, of course, additional improvement. Went from analog boards now to redundant, triple redundant PLCs, for sure. Advanced diagnostics, quicker calibration and setup, improved performance. Yes, definitely improved by a lot, as we now with PLC-based controllers can monitor, diagnose, troubleshoot, calibrate, everything much simpler compared to these analog control boards. So simple questions probably, yeah, the new systems are more reliable, but we still have single point of failures, which are servo valve ESD solenoid valves, if it's not 2 out of 3 ESD, check valves, 1 out of 1 or V to I or I to I converters in a control system, lock in place solenoids, manual valves, hydraulic cylinder. So, and one of the main things is actual servo valve and ESD solenoid valves were actually, where ESD solenoids were addressed with 2 out of 3 ESD, servo valve was actually never addressed. And actually, if you go back, we see that this is one of the most common failures that happens. So, which directly relates to fluid contamination. And of course, we never address hydraulic fluid leaks. So, so from 1960 till today, the single point of failure still remain, and most frequent failures are not addressed. So maybe let's try to address the single point of failures. So let's talk about redundant servo valve manifold. Yes, MEA have done this, and we built these type of units, and you do improve the reliability. If something happens with your servo valve, you can swap it and use another one, and which keeps the unit online. Yes, but it adds a lot more complexity to the unit and adds a lot more cost to it again. So additionally, of course, we can add triple redundant control systems like here and remove all the point of failures within the control system and have an extreme reliability, basically systems on these HPCUs. However, again, cost, it really costs a lot. So addressing fluid cleanliness system. So let's probably try to go the other way. Let's maybe improve the cleanliness and conditioning of the fluid. Yeah, we can actually now use these special online hydraulic fluid contamination monitors, which you can actually monitor the fluid condition, like if it's the temperature, the debris amount, and you're actually able to do it online. So you don't need to run sample tests and so on. You have now very advanced desiccant filters under which you install on reservoir, which really improve the quality of air and any debris coming into a reservoir. You can add a fluid conditioning system for cooling and additional filtration, which is also great. Additionally, you can have the installation of negative 45C temperature protection package, which basically protects your unit and fluid from all the temperature effects. So yeah, we can improve this cleanliness and conditioning of the unit, and it will definitely improve the reliability. But again, it's more cost and more complexity and more items to maintain. So maybe there is any other way we can simplify and eliminate all these failures. As we talk about, there is large reservoirs, there is servo valves, which need to basically have constant failures, and additionally, there is a numerous of hydraulic runs, which usually create constant leaks. Then additionally, you constantly have to replace filters and maintain this hydraulic fluid. So additionally, these units are actually, and I know a lot of actual operators and people within the refinery don't like to work with these units. And usually if something happens, they give us a call right away because they really don't understand it, or it's very, very complex and it's really hard to troubleshoot. So is there other way of actually making it more simple? And we thought about this for years. And 5 years ago, actually, MEA developed a different type of technology, which is called MEA Hawk, self-contained electrohydraulic actuator. So to develop this type of technology, we actually rethought the whole way of how we did electrohydraulics for years. So as we talked about, we had a constantly running motor pump assembly, which took the hydraulic fluid from a reservoir, then charged the accumulator, and then you use this hydraulic fluid to run your cylinder. And you had constantly run your motor pump assembly to charge the accumulator. Where this new unit, we thought about it, and we actually start building hydraulic pressure on demand. So constantly running, and this one runs only when needs to be. And with the current technology and development of all the componentry, we were able to do everything as this unit does in this little rad hydraulic power source. So you got all the performance you need in a much, much simpler package. So how did we do that? So these are the componentry of our self-contained electrohydraulic actuator. So you still have your gearing mechanism, and then you have your hydraulic cylinder with the position feedback, can go on a cylinder or can go on actual either side here on a mechanical override. Then you have your hydraulic power source, and then additionally you have signal and power cables connected to your control enclosure with the HMI interface. So basically, how this unit works is by utilizing a servo motor coupled to the gear pump. So the beauty of these servo motors, these are industrial used servo motors in a lot of automation all around the world and been used for many, many years. And now we are just using it with a hydraulic gear pump. So how it works, we basically can rotate this motor back and forth as many times as we need to, and just build up hydraulic pressure and take the hydraulic fluid, build up the hydraulic pressure and dump it into the other side of the cylinder. So how we can do that is basically using equal displacement hydraulic cylinder. So all we do is basically take the hydraulic fluid from one side, dump it to the other, and just goes back and forth, back and forth. So as you can see in the next videos, you will be able to actually see how fast and accurate this actuator can perform. So after each repositioning, we actually just lock the cylinder with 2 solenoids. And additional beauty of these these servo motors, we are able to operate the RPMs. So we can operate we can change the amount of fluid which goes from one side to the other at any given time. So how it works, basically this is the schematic. So you receive a signal from your DCS. It comes with we compare it to position feedback. We see there is a deviation, and we tell our motor to run one way or the other. So we open the solenoid valves, we start pumping the fluid from one side and dumping into the other. After repositioning, we close these solenoid valves. Whenever we need to go the other way, it just goes the other way. And it just goes back and forth as many times as we need to. Additionally, here is an additional hydraulic power source. So this is just basically additional of these red boxes, I would say. These are actually used only to provide additional speed. So basically, whenever you need more speed, you basically turn on both of the motors and pump more fluid from one side to the other, and the same way around. So whenever you need a very precise positioning, and when it comes just to small movements, you operate only one. And then whenever you need the full, very fast stroke, you utilize 2. So very flexible platforms. Additionally, you can equip this actuator with a fail-safe accumulators or ESD accumulators, which in that case, basically during a power up, you power up the unit and the unit goes through the recharge cycle. So we open these ESD solenoid valves, one for accumulator, one for fail-safe reservoir, and we take the fluid from this fail-safe reservoir and dump it into the accumulator. We dump it and charge the accumulator until the point that pressure transmitter is satisfied. And then whenever it's satisfied, we close the solenoid valves and unit goes back into the operation. Don't mind that I have an introducing here only one solenoid valve. These units actually are able to equip with 2 out of 3 or 2 out of 2 ESD systems, and have different type of logic and hydraulic schematics around how it charges and discharges the accumulator. I know the refinery hate when somebody connects to their ESD solenoids. So if you like more details, I'll be able to cover it in a separate session or questions if you have. So what are the actual benefits and features? So we're still utilizing hydraulics and we still meeting all the performance and requirements for our application. However, additionally, this motor runs only when repositioning, so we save power. This unit doesn't require oil reservoirs or filters, so we eliminated one of the main maintenance issue. This is very compact modular design. So basically, you see we eliminated most of the tubing, and which eliminates the points of leaks and possible locations. Additionally, this unit comes with an HMI screen and very developed controller, which is really really sharp and nice, and you have full diagnostics and troubleshooting and easy calibration as you have with your PLCs. We'll show you the actual overview of the HMI in a bit. Additionally, it comes with a fail-safe mode. So basically, if you need ESD, not a problem. It contains much less parts. As you can see, the complexity of unit is reduced dramatically. It's very adaptable, and it also can be very fast or very slow, as we can actually dial in the speed on the actual HMI and control the pump and the RPMs of the motor. So we can actually always set it up to whatever you need to. So additional benefit, using these type of units, it's actually can operate anything from 120 to 480 VAC, and it takes only about 600 watts while generating the full load. So whenever these units don't require reposition, they sit stationary. And whenever we need to reposition, we basically run it one way or the other, and they develop the full load. That's when they develop all the watts. So it's actually fluctuates depending on the speed requirement of the unit, as for some cases, we need to use bigger motors, which require more power. However, we definitely don't need to run it constantly. Input options, anything for 420, Modbus, Profinet, Ethernet IP, ESD failure, ESD is available. Operating temperatures, anything from North Pole to Sahara Desert, I like to say, so covers all the climate zones, position feedbacks, 4 to 20, non-magnetic, comes with the limit switches. Additionally, these enclosures are hazardous area approved and IP66 rated, so no weather or no hazardous atmosphere can get into these units. Further, we actually compare what our units are capable of doing, and we took the typical FCC performance specifications, and it actually complies with all. It's 100% modulation, 100% modulating service, repeatability less than 0.1%, resolution less than 0.01%. Basically, zero overshoot. Dead time is less than 0.3 seconds. Full stroke can be anything from 5 to 20 seconds, so UOP or accent specs met. Linear thrust outputs and torque outputs are easily met. Basically, all we do, we just change the size of the cylinder and keep everything the same to be able to build up more hydraulic pressure and basically more force. So it comes with a hydraulic hand pump or hand wheel. And fail position and fail last on loss of power as a standard. And of course, the ESD module if required. So let's now talk about redundancy. So we talked about those our HPCUs and about how we still didn't meet the full redundancies without our main manifold to be redundant. Here we actually, even with a single unit, so remember, one we use for precise positioning and another one we use for speed. So here, if one of these modules actually fail, the other one will still operate, and it will actually so unit just becomes slower. It will still operate but become slower. But additionally, you can actually have completely redundant units with a completely separate controls for two units. So you'll have two separate set of controls and running one cylinder, and they will be totally fully redundant and independent. Another beauty of these units is all of these boxes are the same. So they all interchangeable. So you can put one on the other and it won't matter. So we actually, with this type of setup, we got the full redundancy, and you can get it for not that much cost. So now I will have a Hawk interface, so you just get more familiar with how it looks and how easy it's to operate. So I have just one video to run for you. So please watch it.
This is a general overview of the home screen and some of the features that the user will have access to. So on the home screen here, you have local mode, remote, alarms, diagnostics, and your factory setup. You also have a button down here that allows you to log in and out of particular users. You have the factory, the operator, and so forth. First, we'll jump into local mode. Local mode is similar to remote mode in that it relies on a control signal to drive the motion. that control signal must be active at any given time. And it's also a combination of manual, in that the user gets to close and open the actuator using these two push buttons here. And you will have a readout of the local command, which is essentially the control signal, and the position feedback, which tells us where our actuator has moved relative to the command signal that we provide via these two push buttons. Okay. We also have motors 1 and 2, which each has a readout of the RPM and torque that is being output by the motor. So here we'll just drive this back and forth a little bit and get the user accustomed to the screen. One final thing worth mentioning in local mode, you are limited to 0 and 100% as set by the actuator's soft set points, meaning you cannot exceed in either direction what the set points are for the actuator. It is not possible to overdrive the actuator and dead end. For any more detail in local mode, please read the Hawk provided IOM, or rather the MEA provided Hawk IOM. And in the next video, we will cover remote.
So in this video, we just wanted to show you the outlook of our actual HMI screen. However, in the next couple of videos, we will show you actually the control mode where it follows basically DCS signal. These ones are additional screens I wanted to just provide you. These are active alarm screens. So basically, if you mentioned on the menu there, there was an alarm screen. So you basically push this button and it actually can develop the actual alarm and tell you exactly what's happening with the unit. So for example, this one indicates that we lost the input signal. You actually get the timestamp and actual time. Additionally, you can have a history button, which actually gives you the full list of history and alarms you have throughout the whole operation of the unit, which you cannot erase at all. So you get basically the same functionality as your current PLC-based systems. Additionally, you get the diagnostic screens, and this is just a couple of screens from our diagnostics. You have all the readouts on analog inputs and analog outputs or discrete inputs and outputs. So basically, you are able to read out actual signal, raw signal, value, then status and connector point. So you can easily troubleshoot any of the unit functionality right at the screen and see the status. So if there is any loose wire or there is a loose connection, this will turn red and you'll know right away what's happening with the unit. So of course, we didn't end up just talking here about general how these units work. We actually went ahead and tested this unit. So we basically generated a test unit, which has the technical specification of thrust developing 10,000 pounds, stroke 13.8 inches, and speed 1.1 seconds per inch, and did not have ESD function. So this was actually a simulated unit for one of our customers. We basically built identical one that he wanted to put on FCCU slide valve. And we basically created one and just wanted to test it and prove to us and to everybody else that we can do that and we could do it properly. So we also didn't eliminate only with an actuator. We actually created a load cell, which generates, basically simulates the thrust load of the valve. And we actually just connected our actuator to this load cell. And additionally, then we took the FCCU processor licensor specifications. And we were more familiar with the UOP specs. So we took one and we basically start testing our unit to those current standards. So here is a video of actual test setup and actual some positioning accuracy. You'll be able to see what we actually did. So please watch the video. Thank you.
The actuator, the cylinder is currently coupled to a loaded valve simulator. On the front here, we have the dual HPS system, one with the cover on, and you can see on the HPS with the cover off, we've got a motor that's coupled to a pump. And all of that is going to be controlled by the drive that is connected to this HPS via the field wiring that you see. This particular configuration is for testing only, but it still simulates exactly how to drive the actuator. In the middle here, we've got two pressure gauges. Each gauge is going to tell us what the pressure is and then therefore the corresponding load for the extend and retract position of the actuator. And now we're going to provide it a variable control signal and demonstrate how that control signal change will drive the actuator back and forth. Retracting. 1500 psi pressure corresponds to the load required. Incremental extend position changes. On the other side of the cylinder here, we've got a desktop monitor that's replicating the command screen. As the command signal changes, the position tries to follow. Once the deviation between the command and the position has reached 0, the actuator goes into place.
So basically here you see the video of our random testing, and just to show you exactly what we did here. And of course, we plotted all the performance test data, and this is basically a full stroke speed test. And it's basically, as you can see, started from 4 milliamp, go to 20, right in, basically 0 overshoot, right into the dead band, and just go back and forth, back and forth. So additionally, this is the same 25% step change testing. We basically took it and tested it out, and you can see that it hits right in every time and actually follows the curve. Additionally, the one that you actually saw in the video, we actually simulated a random signal. So this actually just follows it, one back and forth. And as you can see, it follows it very clearly and properly operates this actuator valve. So basically test results. So we took these, basically reference the FCC performance specification spec, and we took, let's start with the control stroke speed. So European requirement 5 seconds. This was a, and accent specs 20 seconds. So this unit was built basically to meet customer requirements of 15 seconds full stroke. And yes, we met the accent specification. We didn't met the UP. However, these units can be built to meet 5 seconds per customer request. This was a different request, so we went with 15. Step resolution, 0.1% of input signal change. It passed. We will have a next set of results in the next page. Dead time, less than 0.3 seconds. This one average was about 0.23 seconds, also pass. Dead band, less than 0.1% of the full valve travel, also pass. See the results on the next page. Transient overshoot, we completely pass it. 0% overshoot as lens in the dead zone every time. Stability, as you can understand, this would more apply to a servo valve type of HPCU systems, as to keep it stable. This unit, whenever it repositions to the final destination, just stays there until you tell it to or command it to move. So 0% movement. linearity actually was plus or minus 0.1% of the stroke. So after that, we didn't just run the test. After that, we actually built 4 units and did the FAT testing on the front of the customer. And these are actual results from each testing, and which was witnessed by the end user. And they actually saw all the performance of the actuator, also under the load. So as you can see, step resolution, and we said before, so every time we change the step to 0.1%, we saw the actual movement of the actuator. That time was recorded here, basically about 2.4 seconds, as you can see. That band, additionally, same thing. We ran the test and we saw 0.0 with every 0.016 milliamp control change. We saw the actual movement of the valve, and we actually met the required requirement. So transient overshoot, same thing. Basically, every time we position the valve, it landed right into the dead band. So it's a 0 overshoot and passed every single time. Stability, these numbers are basically, if you compare to what's required, so these numbers actually tend like 5 times better, but I would more consider this as an error rather than any real movement. Same thing with the linearity. Every single time the actuator positioned within a 0.1% of the stroke, and for all the given 4 actuators.
Let's compare our Hawk to traditional HPCU type actuator system. So there is just some few questions. So does Hawk exceeds processor license performance specifications? So as you from previous discussion, yes, it does. Traditional HPCU also. Does it require any filters or fluid change requirements? So Hawk does not require any filters or reservoirs at all. However, HPCU does, which is a major maintenance item. Is the unit self-contained, minimize contamination of the fluid? Hawk, yes. It's a compact modular design. However, HPCU doesn't. Reservoir, they have a reservoir breather and so on. Does it minimize the footprint? Hawk actually does. The HPCU doesn't. It's a pretty big unit which requires a lot of components. Does it have advanced diagnostics? Both of these type of systems do. Available across entire size range. Unfortunately, Hawk doesn't. For some very large valves, especially for expander inlet control valves, there is a speed limitation for Hawk. Even for some HPCU units, it makes it very difficult to be able to operate the valve within 1 second modulation speed. As a result, there is a limitation. For HPCUs, there is no limitation. Common spare parts across all the unit, yes. Hawk have very minimal parts to stock compared to HPCUs. Redundancy available across all components, yes for Hawk and yes for HPCU type system. 80% less parts to repair, service, and troubleshoot. Hawk, yes. HPCU unfortunately has a lot more parts, and we estimate approximately about 80% more parts compared to the Hawk type of actuator. Additionally, Hawk operates only when it requires to move, so you have a major reduced power consumption, and HPCU runs motors constantly. So with that being said, as you can see, there is a major differences between one and the other actuator system, and this major affect also total cost of ownership of these units. So of course, if you have less parts, less components, the total cost of the actuator for Hawk will be much less compared to traditional HPCU style system. Additionally, due to the fact that it's so compact and so simple, it's very simple to install compared to the HPCU style system. As a result, the cost of installation reduced dramatically. Same applies to basically any type of maintenance. It doesn't require filters, not require changing fluid during turnarounds. As a result, there's a major cost reduction over time. And we estimate approximately decreased total cost of ownership by approximately 3 times if you compare Hawk to traditional HPCU.
So after all the testing, and we basically installed 4 units this last year, November 2020, we installed 4 units on FCCU flue gas slide valves. So before it was our units for 26 years. They were great. They worked well. However, a customer would like to go with a newer technology. And since November, they've been in operation and worked phenomenal. It's been working really well, and customer extremely happy. So just to kind of outline these units, we actually developed and built these units for many years now. It's basically 5 years, and we have many installs all over the place. So these are just some different installs that we have. For example, this one's refining oil sands application, which required operation of 24-inch gate valve. And these units been installed in a super cold environment for a very long time now. And as you can see, it's operational, works great. Additionally, it's a terminal inlet, so there is different sorts of rotary valves you can apply these technology with. And this is actually sits on 36-inch groove ball valve. Additionally, you can put these units on actual damper drives also. So whenever you need a lot of torque or a lot of thrust and a very precise control to operate your actual burning process, you can actually utilize these units there too. Steam let-down steam turbine let-down valves, same thing. Basically, can apply these units there. So basically, just to outline and summary key takeaways, there is a lower cost alternative without trades-off in performance, reliability, and safety if you compare a Hawk to HPCU. Yes, HPCU has been around for a long time, and it's sometimes difficult to make a choice of going some other way. However, there is a choice now, and it is our alternative Hawk actuator. So alternative, our Hawk do not require filter changes, oil sampling, has 80% less maintenance items. It's very modular design, decrease possible leaks. Our Hawk also requires less space on the deck, less power, removes requirement of hydraulic runs around the whole FCCU. So sounds like a lot of very cool benefits. So it's also easier to train refinery personnel on because actual unit is very not complex. It's much simpler than you compare your HPCU to. It's basically all the modular design and just a few of the components, which eliminate all this complexity. And of course, with all of these items, a total cost of ownership is dramatically reduced. So hopefully you guys have some questions, and I would love to actually answer it for you. So hide my little knob here. So here, where the advantage in solenoids, hydraulic pumps, servo valves adds, then that have made the Hawk possible where it was not possible in the past. So basically, as my understanding, why there is a way of doing it now compared to why we didn't do it before. So basically, one of the things is actually solenoid valves used to have quite some delay back in the day. Now we use solenoid valves that are 30 to 40 milliseconds opening and reaction time. So, and sometimes you would have to, so you would build up hydraulic pressure and you would not be able to properly control the valve due to the delay of these solenoid valves. Well, now there is actual, we have developed technology in solenoid valves, which are actually able to control and operate that fast. So that's why whenever you reposition the pump, you start building up the pressure, you open up the solenoid valve, you reposition, and you close the valve. And that everything of that can happen, as you can see from our testing here, about 200 milliseconds. And so that's probably the main difference. Hydraulic pumps actually and servo motors are actually located there for many years. And back in the day, MEA actually used servo motors back in the day and utilized it quite some time time. So that was always developed there. It was just basically putting everything together. So next question, what is the difference between the 120 VAC model to 480 model? So basically the difference is that with a decrease in power, you actually have, you are not able to build up a proper RPM for these particular motors. So you lose speed, which is 1/3 of the speed. So if you would like to develop the full speed with a motor, you will need to use 208 to 480. So whenever you use 120, you will lose about 1/3 of the speed of the actuator. So next question. With the hydraulic fluid being directly pumped without reservoir accumulator, are there any issues with cavitation under heavy load stock condition? With the fluid being directly pumped. So basically, we didn't see any issues with that. Because we actually pumping the hydraulic fluid from one side to the other, and additionally, we have actually pressure relief ports at each point of the cylinder.
And the makeup reservoir.
And also, additionally, you have a makeup reservoir of the hydraulic fluid. So basically, whenever you have expansion or retraction of whenever there is a temperature change, the fluid inside the hawk is actually slightly expand or slightly retract. So this way you have just a small reservoir, which provides you this extra little fluid to be able to properly operate the valve, and you don't have any kind of overpressurization or any kind of leak. But additionally, we actually provide a pressure relief valves at each side of the pump. So in case there is any type of pressure spike or anything, we actually dump the fluid from one side to the other and make sure there is no over pressurization. So additionally, if the valve got stuck or you have a heavy load, so basically what happens, our actuator will run and we will trigger the pressure relief valves. And if we won't be able to break that load, or it would basically time out. So it will generate the alarm that the actuator cannot position to the proper location and tell you, hey, motor times run out, and we aren't able to further kind of position the valve. So that way you address it, the heavy load. However, you do not break the valve because you have a pressure relief valves. Can you go over the fail? Excuse me. So here I'm together with our director of engineering. So I just have a quick note here.
Yeah, if you wanted to jump back to question one, one of the things is more cost-effective leak-proof solenoids have become available, and more effective micro pumps, cost-effective micro pumps have become available. Those are probably the two key drivers of why this technology is, I'll say, producible, because it's cost-effective now.
So here I'm actually sitting with our director of engineering, and he would like to he wanted to address the first question about why these units became available at this point in time, and why they were actually developed only in recent years compared to the older ones. So Mark, please go ahead.
Primarily more cost-effective low and no leak solenoid valves have become available. Previously, zero leak and low leak solenoids were, I'll say, prohibitively expensive. The other technology change or shift has been, there's a whole field now of what's called micro pumps, where these very small displacement precise pumps are available, and they're also available cost-effective now too. And those were kind of the two things that allowed this technology to come, in a cost-effective package. I mean, things like that were available in the past, but it was always cost prohibitive.
Yeah, thank you, Mark. So hopefully that also develops and answers your full question. So the next question, can you go over the fail close position on the loss of power scenario and how it differs with a traditional HPCU with the redundant reservoirs? I'm not actually familiar with redundant reservoirs. Oh, you're probably talking about accumulators. So actually, so current units and actual specifications on UOP and Accent specs calls out that on the loss of power to the actual controller, the unit have to lock in place. So basically, if you require fail clause on loss of power, we would have to provide additional accumulator or reservoir, which would operate with the solenoid valves, which can be separate from ESD system. So, however, it can also be combined with it. So this is basically just looking into different variations and making sure how you want your actuator to operate. However, if you're talking about current setups, we would have the separate ESD system, which would trigger the ESD function. And then whenever you require fail clause on loss of power scenario to the actual controller, there would be probably a separate system and separate accumulator system, which you would charge also before that. However, yeah, for this particular applications on all the FCCU slide valves, we just require to fail last and loss of power. Like currently, our HPCUs does the same thing. It doesn't actually go fail close. It usually stays put in 99% of the actual cases. Since there is no next question, since there is no reservoir, how do you track or detect slow leakage of the circulating fluid? Is there nitrogen pre-charging for the accumulators? And what is the composition of the hydraulic fluid? Is it water-based? So since there is no hydraulic reservoirs, how do you track or detect slow leakage of the circulating fluid? So basically, at that point in time, you would probably see the level indicator. So there is a level indicator inside this actual little red box, and actually we can install one which is outside for you, which is in the little kind of additional reservoir, which actually will show you the amount of fluid within the unit. And at that point in time, you'll be able to see if there is any leakage externally. However, internally, you would see the operation of the actuator start basically faulting out, or you would not be able to position the valve as well as it should, because it would start basically trying to catch the position or trying to position the valve. And if you wouldn't be able to, you would actually be able to notice it from the diagnostics and stuff. So additionally, these actually can come with the pressure transmitters, which can be also monitor the actual pressures inside each side of the cylinder. As you saw on a video, we had the pressure gauges there. We can actually install with the pressure transmitters, and you can actually monitor the developed thrust and pressure of this unit, and you can actually track it back to your DCS, or we can kind of alert you if there is something unusual going on, or if we're not able to build up enough pressure to position the actuator. So probably the only thing which can probably leak by is actual piston seals. So hopefully I answered that question. So have you installed the system in FCCU flue gas? Have you installed the system in FCCU flue gas slide valves? Yes, we did. As you can see on a picture, we installed 4 units in November 2020. So it's been what is it, 4 months or so. So next question: have licensor like UOP endorsed the Hawk solution for FCCU slide valves? So we actually discussed with UOP, actually talk to them and show them this unit. And basically how it works, the certification is you have to install the first unit, you have to prove the performance, you have to do the test data. And that's what we actually were doing. And we now have to wait about a year to be able to come to UOP with the actual letter of recommendation from the refinery. And then we will be able to kind of approve it on the specifications. So this is basically what we're striving for, and that's what we are going to do in the future. This time, we presented the technology as an alternative, and in the future, we expected to put it on actual UOP specifications and as a part of compared to traditional HPCUs. So next question, do you have the ability to auto-schedule partial stroke testing for ESD application, and can you collect diagnostic information, the PST testing for predictive maintenance? Simple question, yes, we can actually do that, and we can test these type of we can include this type of feature. This is additional feature. However, yes, that's quite simple, and we can do that. And you can actually send this signal back to the DCS and actually track this type of kind of repetitive partial stroke testing. But for HPCUs here, like if we're talking about actually ESD system on the current FCCU setup, we want to do it online testing and making sure everything works. So this is basically just a part of ESD system for these FCCU type of hogs. Some HPU systems have the ability to stroke the valve 1 to 2 times with accumulator. How this is handled with a hawk actuator? So this is not so due to the design. We do not have accumulators. Usually you're able to stroke the valve with accumulators, right? On HPCUs here, you do not have that ability. You have only a hand pump or a hand wheel to do any manual operation. But with this, I would like to ask you a question. So when do you really operate this unit in a manual mode, or whenever you need to stroke it 1 or 2 times? It's really only the ESD portion which requires really to close the valve and making sure that it's 2 times the volume and making sure the valve closed. And if you have additional stroke or any ESD event, you need to close it. But whenever there is a power loss or there is anything else, that valve is locked in place anyway, right? So, and I personally, I've been working for MEA for over 6.5 years, and I used to work a lot in the field service, and I have not seen a request where there is a power loss or something and you're actually using this hydraulic energy to position the valve. It's only unless you really lost the power to the motor or something. So I just don't know this scenario. Maybe you guys do. So if you do, please let me know. I would like to know that.
During normal operation.
I'm sorry, just Mark has a comment here.
During normal operation, the accumulators are not required on the system. In other words, we can meet the speed requirements without accumulators during normal operation.
Yeah, thank you, Mark. Well, additional comment is that you use accumulators only to generate the speed on these HPCUs, right? So you don't really need these accumulators on this unit because it can generate enough speed for a normal operation. That's pretty much it. Because so next question, do you have a SIL 1, 2, 3 certified models for ESD applications? This is actually one of the things that we run into quite often. So usually we utilize SIL 2, or I mean actually SIL 3 solenoid valves if it's required. And actually at this time, we are going through this type of calculations of looking into certifying our ESD system to SIL 3 or SIL 2 or SIL 1, whatever we can get. But now, right now we're working on it. What is Hawk system useful life? So usually we talk about 20 years. But you need to recommend to rebuild the units and change the soft kits every 5 years. So basically change the pump, change the seals, change the solenoid valves every 10 years. You would have to go through the full rebuild, probably replace all this little red box, replace the control components, and that's pretty much it. But yeah, you should expect these units run for about 20 years without any other. But you of course will need to do the maintenance. I mean, you need to do that. So since the Hawk system is self-contained, there is no central HPCU. What is the interface between a given Hawk system on one slide valve and the rest of slide valves? How does the ESD or trip interface look like? I'm sorry, 1 second. Let me read this again. Since the Hawk system is self-contained, there is no central HPC. What is the interface between the given Hawk system on a slide valve and the rest of slide valve? Well, it's basically just receiving signal for its 20 milliamp signal, right? So you have actually a unit right here, actually on the back. I can you just basically feed 4 to 20 milliamp on these cables, and then you basically receive a signal, and it operates exactly the same way as HPCU. So nothing crazy, nothing particular. It can actually send out the Modbus signals to you if you need to, if you need any alarms. How does the ESD or trip interface looks like? So it's the same way. Basically, you have a ESD signal coming from SIS system to the solenoid valves, which basically, whenever a refinery have a trip, it basically removes the power to the solenoid valves, which trips the system. And we actually will not be connected to ESD solenoids. We just actually be connected to see if you have an ESD trip. We are not, we don't want to interfere any of your ESD solenoid functionality. And we just gonna notify our hawk just to make sure you're not run the other way or anything because there is an ESD trip. So if the FCC unit trips due to loss of power, slide valve must shut. For example, sometimes slurry pumps or MEA are electric and unit will trip due to the low flow. Well, if your FCCU requires to shut on loss of power, we would just basically use the accumulator system, which is basically would open up the solenoid valve and dump all the fluid into one side of the cylinder and make sure the valve is shut. So the same way as ESD system would work on these units. So do we have any more questions, guys?
So Taras, we're actually out of time. I will be sending up a wrap-up email to everyone who participated with your email address. So anyone who has additional questions can contact you directly. So thank you so much for that excellent presentation. This is our last webinar that we have scheduled for 2021. If you do have something to share, I would love to talk to you about that. I would like to get a few more scheduled for the second half of the year. So please contact me. And then also just a quick reminder that we are going to be producing REFCOM 2021 the week of May 10th through 14th. Taras and MEA will be presenting and exhibiting at that conference, as well as many other exhibitors. We do have great registrations so far, so please consider attending. We do have a couple of free passes still available for FCCU personnel from refineries. Please contact me to make sure that those are still available for you. And with that, we'd like to thank you for attending today, and we look forward to seeing you at one of our future events. Have a great week.
Thank you.
Thank you.